Okay, so good evening and welcome to all the 31 participants in this meeting. So we are delighted to have the Chief Patron of NACDeC, Dr. Kota Harinarayana, who needs no introduction amongst the aerospace community. He has very kindly volunteered today to talk to you about electrical aircraft and electrical propulsion systems. And we are live on YouTube also. Link has been shared on the WhatsApp group. All your friends who are not in the NACDeC competition are welcome to attend from there. So, Dr. Kota, over to you now.
Thank you, Professor Pant. Thank you. And nice to have all the young people attending. I hope my voice is clear.
Loud and clear.
I'm just seeing whether let me go back to presentation mode. Yeah, now I'm there. My topic today is basically introducing the idea of electric aircraft and what are the electric propulsion systems, because we are very familiar with battery, but battery is only one of the propulsion systems. I thought we need to share and discuss about what are the electric propulsion, what is the exciting things that are happening, and how important it is for a country like India, this electric aircraft and the propulsion system. This would be my topic. Let me now move forward. See, civil aviation itself, there are growing challenges. Everybody, all of you are aware of the global warming, and the situation is close to alarming, and the problems are escalating. So there was a decision taken that the main cause was the carbon dioxide. There are others also, that by middle of the century, 75% per passenger kilometer, the reduction in carbon dioxide should be done. It won't be that easy because there is a continuous increase in global traffic. In fact, the traffic is fastest increasing in a country like India. So the small improvements, a lot of improvements are occurring by improving the combustion engine, gas turbine engine, but that won't be sufficient. Just not possible to achieve this goal by them. So there is a need for a radical change. So a radical step change in technology required to meet the targets. And another challenge civilization faces with available crude oil, because the source of conventional jet fuel itself is coming down. So the studies show by 2030, the price will increase quite a bit. Today, in something like $80-90, but it will come to $130 at least. And so this is the situation worldwide. And let us see what happens to us. So what is the way forward for civil aviation? See, all of you are now aware of the road transport, similar challenges as it is, it depends on fossil fuels. To combat these challenges, battery-powered hybrid vehicles featuring less or zero emission already entered the market. Entered in India, entered in China, entered in many parts of USA and Europe. And a lot of investments are being made to develop more efficient lightweight batteries and also fuel cells. We are going to discuss about both the things. The key question for civil aviation industry, are electric propulsion viable for transport aircraft? This is the point. This is what is the question that is being there. As it stands today, that is small aircraft, it is okay, but the bigger aircraft, it is still not all right. Let us see. As we go by, let us see what it is. As of today, pure electric propulsion suffers from significant performance and weight challenges. And electric powered aircraft are limited to, as of today, as I mentioned, small and general aircraft. Maybe UAM are one of those which are being considered in a big way. But due to rising fuel prices, regulatory and public pressure to limit air traffic emissions, introduction of electric propulsion, not only on small aircraft, but large, is no longer an option, but a necessity. And studies show that incremental investments and focused R&D could result in entry of electrical but challenges are many to be addressed. This is what let us examine today. This would be of interest to all of us. What are the challenges of India? One is the rising cost and availability of crude oil as a source of conventional is a challenge, because we import 90% of our crude oil. And that's what I said, needs to find alternate energy sources. India, another important, India is already the third largest domestic civil passenger market in the world. And by next year, we are expected to be third largest civil market. That means both domestic and international. And enhanced connectivity is vital for economic development. We are a growing country, economy is developing, and this air connectivity is an absolute must. So there is no alternate to that one. So it is essential for India to harness alternate energy sources to contain these greenhouse gases while catering to growing traffic. Anyway, that is the basic part. This is the crux of the problem. What are the benefits? All of us have heard here, there, but I am trying to put the whole thing together. Today, there are around 200 companies, maybe more than that, around the world investing in startups and projects to develop all types of electric, from retrofit, hybrid, electric general aviation, to long-range commercial planes, to eVTOL. That's what we are going to talk a little more, urban taxis and all. The electric aviation movement gaining traction quickly, especially as the industry faces mounting pressure, as you said, to reduce harmful emissions. But beyond the obvious environmental benefits, there are other compelling advantages, advanced electric. Here are the things. This is what is important for all of us to know. Number one, reduced fuel. For some aviation, the decision to pursue electric propulsion is driven by potential cost saving, not necessarily environmentalism. Fuel costs are a major variable expense for airlines. As prices rise, so do the cost of tickets per passenger. High fuel prices are a significant expense and barrier to flying more often. The introduction of a hybrid or all electric is a step towards making flying more affordable for everyone. Most of you have seen 45% of the direct operating cost in India is fuel alone. So it is much more a challenge here in India, whereas around 25% is in the international market. Now, for example, it's from Aviation Week, I have taken this out. There is a Beaver, a DH-2 de Havilland B sealed plane. It was modified a couple of years back to run on NACDeC 750 horsepower electric propulsion system with a 4-blade Hargel composite propeller. It's a well-known propeller. The electric driving costs about $12 per operating hour compared to piston motor driving, which ranges anywhere between 300 to 450 per operating hour. See the cost difference. It looks to be too much difference to believe, but that's what it says. Aviation is another all-electric aircraft. I expect to offer operating cost about just $200 per hour, about 1/5 the cost of a similar turboprop. So we are talking, in addition to emission benefits, the cost of operation likely to be low once the technology matures. Compared to jets and turboprop aircraft, electric are much quieter, sometimes nearly silent, electric especially, have the potential to operate close to cities and at all hours of the day without disturbing communities and wildlife. This is important as the cities are growing and the airports are close to the city and the disturbance is too high and people are objecting to it. Even in India, people are objecting to. So this is an important issue. But in Europe and all, there is strict regulation. Beyond at night, 10 o'clock or 11 o'clock, you are not allowed to fly. But with an electric aircraft where it is silent, you can fly 24 hours. That is the benefit. Now, there is another important point. That is reliability. Motors are much simpler compared to internal combustion. There are fewer moving parts, making them less susceptible to wear and more reliable. The hope is that electric aircraft will require less downtime for maintenance, reduce operating costs. So the maintenance cost will come down. So maybe as and when we come to a reasonably mature state, this will be what is a very important factor for all of us. Globally, aircraft account for about 1.5 to 2 per emissions. But what we have to remember is that at higher altitude, the impact of this is sometimes 3 times what happens when you are underground. So this is an important. So with the tech startups and established joining forces, fossil fuel electric is quickly transforming from a future vision to a reality. This is what is important for all of us. Now, you are all involved in aircraft design. But let's see what are the challenges. Electric propulsion aircraft leads to new challenges. What are they? For conventional aircraft, large statistical database and component weight, geometry, performance, system category is available from many previously designed and built aircraft. For electric, no such database is available. And configuration system cannot be generated based on statistical data. But statistics are very, very little. So we need to know how to go about it. Even the regulation do not cater to electric propulsion. You have to read across. There are no clear-cut regulations today, whether in Europe or USA or anywhere. Okay, and this is a challenge. The way energy is stored is also totally different from conventional energy, because fuel we are kerosene we are storing in wing tanks, and when you store that has a significant impact on structural design. It is a relieving load. A lot of some of you are structural designers, you will agree with me. Operational electric are also different. The conventional gas turbine propulsion direct dependence on ambient conditions, density, temperature, and aircraft continuously loses weight due to fuel burn. But electric propulsion is totally different because there is no weight reduction, hardly anything. That impacts the performance. So in your modeling, in your thinking, your calculation, this is an important issue. And there is a need to modify. Suppose initially you have to modify an existing aircraft to carry out a series of experiments and generate data for updating the model to size aircraft. This would also enable assessing safety and life issues. These are the important things. Because we don't have database, we have to create database, we have to work out safety issues, we have to see how the system is going to perform. So these are the challenges of configuration design. This is what you have to keep in mind. Now, let us just, I don't want to spend too much time, but this single slide I want to say what are the zero emission technology. One is what you call biofuel, synthetic SAF, what you call, where your conventional fuel is replaced by biofuel. Here, carbon dioxide intensity comes down depending upon source. Air quality, NOx and particulate matter emissions similar to diesel, which is there. Total cost of ownership slightly different. Okay, powertrain same as combustion, no different. Constant almost same as the existing one. Refueling same, almost same. They're not much different. You can use existing infrastructure. This is the benefit. Okay, why if you go for biofuel. Now hydrogen internal come. Now hydrogen itself can be used instead of aviation fuel. So here again, minimally for it is a green hydrogen if it is there, and there are no significant NOx emissions after this treatment. What is written, 30% for renewable hydrogen H2 production, about 30% more or so. But H2 engine with similar capex as diesel, but you need H2 tank. The tank requirements are different here. This is a challenge. But engine with same size as today. But as I said, tanks are required. It may take a little longer because the volume, it is 4 times the volume. Though energy content is much higher, but the volume is higher. So you need more time for the fueling that one. Okay. But infrastructure, you have to create the hydrogen infrastructure. Now let us see what you call the fuel cell. A fuel cell is operated by hydrogen or another what you call like ammonia and all, which have the hydrogen content. So here, of course, zero minimal. If we are getting hydrogen, which is a green hydrogen, no emissions. Air quality is good. About 35% for renewable, high capex for fuel cells and batteries, but more scalable than the other one. More space needed than combustion engine for fuel cell and a hydrogen tank. In the aircraft, you need more. And roughly because you are using hydrogen here. Refueling uptime is almost the same as previous one. And hydrogen distribution refueling infrastructure is required. That needs to be created. It's not a minor point. It's there. Then battery electric, all of you are familiar. Carbon intensity depends on grid mix. Zero carbon dioxide using renewable power. Zero emissions. Efficiencies. See, efficiency something like 75 to 85%. See, all others, so we are talking 20, 30, 35. Here, 75 to 80%, depending on transmission. This is a major improvement. Okay, efficiencies are very high, and lot of high capex. If large batteries are required, of course, would be higher weight. This is a major problem. Higher weight, higher volume. So as a result, there is a payload restriction. This is the thing, and refueling. It is big challenge. Fully, you want to charge, it may take 3 hours. People, a lot of work is going on. How to do fast charging, but this is a challenge. And charging infrastructure and grid upgrades are required here. So benefit here is high efficiency, but all other aspects we need to look at it. So this is broadly, if you look at it, the hydrogen fuel cell generates electricity. Battery also stores electricity and supplies. So these are the two areas, fuel cell and battery are really what you call as electric propulsion system. So that is what we'll consider now. Now here again, I'm putting to you the efficiencies because this is important for our the thermodynamic cycle. The best performance efficiency for a kerosene turboprop engine 50%. In fact, quite often most of the engines I have seen, they are much less, maybe around 40 and all that kind. But the best you can get is 50. Gearbox almost 98%. Propeller around 80%. That is what it is. Okay, so you get overall efficiency of 39%. Turbofan, you get about efficiency of 50%. Fan and nozzles are around 65%. So overall about 33% is the efficiency. Battery, as we discussed, it's 100%. Battery, if you are considering, then controller is 98%, electric motor about 95%, gearbox about 98%, propeller about 80%. It varies a little bit, but 80% is what? The overall efficiency, if you see, it is 73%, almost double that. Fuel cell itself is about 60%. Unlike battery and all, it is about 50%, but better than the what you call turbofan and turboprop. Controller, all of them are very high efficiencies, but overall you get about 44 efficiency. So these are very important parameters which all of you must keep in mind. I just wanted you to see this one because this particular graph shows you two things: mass specific energy, watt hours per kilogram, and volume specific energy, watt hours per liter. Okay, these are two important parameters for an aircraft. If you see here, see battery I have shown in red, and I've shown here hydrogen, ethanol, kerosene. If you see mass specific energy, the difference is a factor of 60 between the battery, lithium ion battery, and what we are talking about, the kerosene, what is the conventional fuel. And volume wise, a factor of 80. It's a massive thing. How do we cater? This is the challenge that we have to see how to do. Of course, a lot of improvements are occurring in the battery technology, but it will take years, okay? And we need to see how to handle. This is the challenge what we have to do that, okay? And let's see the next slide. Well, I was talking about what you call various ways of doing. Let us just single slide only I'm showing what are the, one is hybrid electric, that means fuel, gas turbine, gearbox, okay, and then propeller and all that one, EM, what you call, okay, electric generators, then hybrid generator, then you go to what you call power management, then electric, what you call machine generator converted, then fuel, rotor, or a propeller, rotor, fan, and water. This is what you call serial hybrid electric. The parallel hybrid electric is, you have a gas turbine engine, okay, you have a battery, and the battery is now connected to the gearbox, okay, that is what it is there, parallel. Now, we have, let us see, electric, full electric, you have a battery, you have a power management system, you have got a electric generator, motor, generator, then motor, then gearbox, then rotor. The alternate one is you have no gearbox here, you have a battery, you have power management, then you have electric motor, the EM is electric motor, then rotor. So here the motor controller is also going to control the rotor RPM. Okay, both can be matched together. In fact, the benefit here is no gearbox. The gearbox is a heavy fellow. So here they are trying to get rid of the gearbox. So that is the difference between the two. I was talking to you about a fuel cell. You take the hydrogen and supply it to the fuel cell. Then you have a power management system. Then you have a motor, gearbox, and that will operate the rotor. Okay, it could be a propeller, it could be a fan, it could be anything. Then you have a what you call a hybrid electric. Here the hybrid is fuel cell plus battery. It's an important thing. The fuel cell is hydrogen is injected into fuel cell, and fuel cell is producing electricity. Battery is also supplying electricity. Both are controlled by the power management. Then that goes to a motor. Motor goes to a gearbox. Gearbox operates rotor. Okay. So if you see the RR2, full electric, fuel cell, and fuel cell plus battery, these are the kind of things which are basically electrical propulsion. There are others, the earlier ones are hybrid, and they have their own disadvantages. They can be starting point, but this is what we are considering as electric propulsion. Now, today, what is the state of art? The thinking is by 2025, say 1 to 2 seats, small aircraft possible. Okay, that in fact, today 1 or 2 aircrafts are already flying, and so they are yet to be certified, but another couple of years they will get certified. Okay, so that UAMs, which can carry say 1 or 2 passengers and all that kind of thing, or unmanned or cargo or emergency van, what you call medical, all of that can possible. We could do that. Okay, lot of other challenges, but it looks to be these are the kind of things with a small range, maybe 100 kilometers or so, looks to be it is possible to do. These are the things which appear possible in next 2-3 years. The next one is what they call as a hybrid. They say another 5 to 10 years, maybe up to 15 to 20 seats. It is possible. A lot of work is going on. Already there is a 19-seat aircraft with 1 engine, conventional engine, another with the hydrogen powered. Things are going on. So it may take another 5 years or so, but that seems to be by 2030, it seems to be possible. And hybrid, another 10 years, even 100 seats are possible. The prediction is that about 70, 80 seats, 50 to 80 seats, full battery or fuel cell powered aircraft, it may take another 5 years, but 35, 40, that's what we are telling, is possible. That's what we are. In other words, what we are telling is another 10 to 15 years, a fully electric aircraft is possible. When I say electric, battery or battery plus fuel cell, okay, that is what we have. But battery has certain challenges, fuel cell has certain challenges. Let us see how it can be combined together. It will give you a benefit. But small aircraft, today it is possible. Large number of them are flying. Only thing is they need to be certified, because even certification standards are evolving now. So let's see what we move forward. So what is possible, what is going on, a lot of work is going on, is the urban air mobility. Okay, is a new, safe, secure, and more sustainable transport for passengers or cargo in urban, enabled by new technologies, integrated into multimodal transport system. This is important. The transportation performed by electric taking off and landing vertically, remotely piloted or with a pilot on the board, even remotely piloted. That is what we are telling. And the ESA, the European, they are expecting by 2025, it will be fully certified, will be available. To me, it looks to be quite a feasible thing, and the rate at which work is going on, it should be possible. And we should be able to at least fly a 2-seater aircraft in India in another maximum 2 years. Okay. Now, Now, I want you to see this figure. These are the 3 UAM vehicle configurations. The first one you are all familiar, where there is no wing there. You are a multi-rotor configuration, large number rotor cell. It may not be quadrupter, it's multi-copter because of the certain redundancy requirements. A quadrupter may not be a viable thing, but a hexa, octa, all of them can be there. The other fellow is a vector thrust concept, where you while take off, vertically taking off, the whole wing is rotated, it goes up. Afterwards, the whole thing is rotated opposite direction, and you fly. That is the vector thrust concept. Either wing or the motor itself, it can be rotated. The third is what you call, you have dedicated what you call propulsion for lift and dedicated propulsion for cruise, and you manage them so that you work on that. These are the 3 basic things, configurations, which are now, if you see everywhere, these are the configurations which are being considered. And let's look at these things and see what are the plus and minus benefits of these kind of things. Okay. Now, these are what we talk about configuration, but you need energy, electric energy. So storage of electric energy is a crucial parameter. So for electric propulsion, large amount of electric energy have to be stored safely and readily available on board. In principle, various technological storage exist. The most common are batteries, fuel cell systems, as we discussed, and also capacitors. But there is a difference. Capacitors outperform that power. Instant power, you want power. Power per unit weight, capacitors are there. But very, very inferior in their weight, speaking of energy storage. Very little energy they can store. So capacitors are used for very short, a few seconds, where high power is required, very high power, and that is used. In contrast to that, fuel cells mark the other extreme. Fuel cell is only energy converter. It is not storing energy. Hydrogen goes into fuel cell, the fuel cell converts into energy. So energy is stored externally. So mostly in hydrogen, the light hydrocarbon fuel. But hydrogen is the best way, but there are other things. In long-term low power application, fuel cell is good. Low power, like after the takeoff, after climb, after there, and you are cruising. At the cruise, you may need only half or even 40% of the fuel. There, you can use a fuel cell. But for initial, what you call takeoff or climb and all that, you need a lot of power. So fuel cell is not a good fellow. So therefore, higher power demands, the fuel cells do not reach the weight specific for capacity of batteries. So a combination may be a good thing. That is, power and energy characteristics, if you want to come, the batteries are in between fuels and capacitors, providing a compromise between weight specific energy and power. Let's see. So these are the typical, one is the battery, most of you are aware there. Okay. You have the battery pack. We'll talk about a little more. We are talking the DC AC, because motor needs AC power, battery supplies DC. So you convert that, and the motor operates the propeller. This is the simplest of them. Other option is you have a hydrogen tank, supplies fuel to and get into fuel cell. Again, you need to have a DC-DC converter, which goes to a bus, and to the bus connected is the battery, and from there it goes a DC-AC converter. Then you have a motor, and motor operates the propeller. These are typical. There may be minor variations. For example, I have not shown any capacitor. May not be required in all cases. Okay, now let us look at the battery. This is, all of you are very, very familiar. Okay, today the state of art is about 150 to 170, even 200, around that watt hours per kilogram. And already there are a number of cells. This is at cell level. Okay, 300 watts. And pack means when all cells are put together, battery management, put everything, you lose something like 32% of capacity for the same weight it comes. So battery pack is heavier because all these things have to put. So this point you have to keep in mind. Okay, what you talk of cell is not that you have to increase the weight by another 30-35% when you talk about pack. So that is what you have to keep in mind. We'll be talking with cell, but you can't use a cell, you have to use as a battery pack. Now, what are the performance battery cells? This is important for us. It will depend on discharge profile and environmental conditions. The energy storage capable battery defined by the discharge current and cell voltage. As you see in this pen, V into IT into DT, that is the energy. The voltage provided battery thereby not constant, but reaches the electrodes redox, but only if the electric circuit is not closed and the current load is zero. But that is theoretical. It is therefore called open circuit voltage. Connecting the cell to an electrical load, a cell voltage drops. So you have to be very clear what is the voltage when the load is connected. And second important point, this is very important for all of you who are designing the propulsion system, is a battery cell gets discharged at a certain rate of discharge, or in short, we call it a C rate, which expresses the discharge current relative to current required to discharge in 1 hour. Okay, this means 1 hour current typically at the rated capacity of cell in ampere hour. Well, let us see an example. If a battery cell has a rated for 10 ampere hours, if a discharge current is 10 ampere, it represents a C rate of 1. A 20 ampere, if I'm drawing, it is C rate of 2, double the rate of discharge. Okay, this is an important parameter you have to keep in mind. Okay, people always talk what is the C rate, but your use may be higher, it can be lower, and that depends the capacity of the battery. Okay. So now let us see what are the things. State of charge is this charge status of battery. That is what you are interested. Okay. The cell should not be discharged below minimum cell voltage. If you discharge below that, what happens? This is called a cutoff voltage. It will get into corrosion. It will get into damage. The battery cannot be used. So a lot of other problems go. Some roughly they say about 20% is below that you should not go. And there is a second fellow called temperature effects. Rate of cell rate depends on temperature. Up to some temperature increase, the rate of cell reaction increases. But beyond that, it gets damaged. And rate of diffusion also rises with temperature. Okay. So above some battery cell degradation, up to some 40 degrees centigrade and all. Okay. But if you go beyond that, then there is another big problem. All of you have got a car or a scooter. If you have kept that battery for a long time without use, it leaks and it becomes a dead. So you have to be careful. Okay. And another important point is called cycle stability. A cell depends on operating history, temperature effect, charging discharge, beyond voltage, and depth of discharge. So these are the fellows. All this must be considered when you say that is the size of my battery, how much or what endurance I can have, how much distance I can have. So this is a fairly what you call complex game. And that is what battery, while simple, but complex, challenging. And heat output, capacity losses occur during discharge of battery cell are mainly dissipated as heat. And that heat causes a lot of problems. The amount of energy extracted from is affected by internal losses due to discharge currents. Increasing discharge rate, that means power losses increase and less energy is extractable. If your discharge is very fast, less energy is there to do. So energy store capacity, power output are interdependent. Extremely important point. If I'm drawing more power, my energy storage comes down. This is an important point all of you have to keep in mind. So far, battery characteristics were described on cell level, but a cell you can't use. A system battery cells, including control, is necessary to provide required power to that battery system. Okay. So operating voltage, range of single depends on putting them in series. And if you want more current, you put in parallel. But a series parallel combination, you put it, you get what you call the required voltage, required current. And that is what you call a battery pack. Okay, this is what we mean by battery pack. I showed it in a very simple way, but this is what actually happens. Let us see 1 minute we should spend on what are the regulations. This is important because this is what governs how we are. Because this regulation apart from safety point. The storage must be designed and installed follows. Safe cell temperature and pressure must be maintained during any probable charging or discharging condition. No uncontrolled increase in cell may result when the battery is recharged previous couple, at maximum regulated voltage or power during a flight maximum duration, under most adverse cooling conditions like occurrence. This is an important fellow. This is the fun which we have to meet your UOM and everything. So that means you need a battery management system. This is what in order to meet these requirements, battery has to be monitored and controlled by battery management system. The system ensures that cells are operated with their specification during charging and discharging. Otherwise, operation beyond the cell specification could result in damage. Cell ranging from reduced service lifetime to excessive heat production and fire hazard. So depending on the cell type and required level of state, voltage, current, temperature, state of charge, state of health of each cell in the pack is monitored by a battery control system or a battery man, BCU or battery man. So this is a very critical for operation safety. And so BCU ensures that the current load of all cells is balanced equal between cell to cell in order to protect single cell from overload condition and associated damage. If any cell approach exceeds the operational limit, BCU is capable of disconnecting the respective cell or the whole pack from the electric grid to avoid the further damage to cell. Here, for example, I have given you 3 groups. If some damage occurs, the whole one group is removed so that the whole system is now safe. So this is what you call a battery control system where they have got a master-slave concept and all. Okay, just to give you an idea about what this is a very, very critical fellow, and no use of having a battery without a battery management system. See, batteries are now used extensively in cars, and that's why the battery development is accelerating, which is good for us. Okay, and for small aircraft or UAMs, maybe these things are good enough, some improvement. You can see Tesla and a lot of good things are happening. A lot of batteries, a lot of packaging. You can see some of the battery capacities, turbo weight, range, and all those kind of things. They are relevant to us. And here are the kind of models of that, the BMW, different aircraft. At the bottom, I have given that for your information. You can have a look at it. Okay. Now, we have been talking about lithium-ion batteries because lithium-ion batteries are the ones which are being used now in all the most of the what you call ground vehicles. But there are others: aluminum air, magnesium air, zinc air. And they are called flow batteries. They have a lot of benefits. A lot of work is going on because, for example, aluminum air is called a primary battery, and other things are also there. Okay, a lot of work is going on, and they have their own benefits. We'll not go too much in depth into that. So there was a NASA 4 years old, but still relevant. If you have a cell 250 watt-hours per kilogram cell level, pack level, as we said, for 30% you can remove. Okay, for 2 to 3 passengers. Okay, VTOL, 40-50 miles, all electric. This is the kind, and that's what is now happening. You see, this is what is happening in the world. But lately better now is something like 10 passengers, lot of work is going on, where battery is of 400 watt-hours at the cell level, 300 watt-hours at the pack level. Okay, then. Now, next we are talking another 8 to 10 years. We are talking 600 watt-hours at the cell level, 4 to 500. Here we can do something 50 to 70, but a conventional takeoff and land. Okay, and hybrid electric. But I'm talking about pure electric. Possibly this can be done, but the range is lower. If you want bigger range, okay, then we have to see how to increase. So this is extremely challenging, but it looks to me, the last one, what I've written, a lot of technology development has occurred, a lot of acceleration has occurred. That is the next slide I want to show you. This is what is a company called Amprius in USA. This is what they are producing. And silicon carbon composites technology, they're talking about energy density about 750 to 900 watt-hours per liter. Okay, here, but whatever energy density 280 to 350. But lithium metal solid state, here they are talking of 350 to 450 energy. This is what is the specific energy, and they are now talking about silicon, but 400 to 500. That is what they are talking about watt-hours. Okay, this is what it is. Seems to be good. Already they are doing pilot commercial is already going on. So it looks to be the rate at which the technology growing is going faster than what NASA predicted about 3-4 years back. So we could expect things will happen pretty fast. Now, let me talk a few minutes before the fuel cell It converts the chemical and in a fuel to electrical power without any combustion, no exhaust from fuel, totally carbon free if hydrogen used as fuel. If you use some other, then there may be, but there is no NOx or anything like that. Hydrogen seems to be either in liquid form, gaseous form is what you use. Already there are many units, there are experimental stage auxiliary power, most popular. Low altitude aircraft propulsion power, high altitude long endurance aircraft, airport application, ground support equipment, unmanned air vehicle fuels are being used. I'm just going to show you one picture. This is the fuel cell for an air. Almost some 8-9 years back at DLR, Germany, they are built for operating the nose wheel. You can see here all the elements of a fuel cell. That's why I'm showing this picture to you. You have a small fuel cell is a small fellow, but around which big paraphernalia is required. You need a hydrogen tank, hydrogen recirculation. You need a small battery, as I will talk to you, for operating this fellow. Then you need a cooling unit, you need a blower, you need a converter, and you need a control unit. So this is the full pack. So this is basically the kind of thing what we are talking about there. So which is not just the stack, but the paraphernalia which has to go along with that. What are the characters? There are two main types of what you call fuel cells. One is called proton exchange membrane. It operates at only 80 to 120 degrees centigrade, fairly low temperature. But there is solid action fuel cell. It operates at very high temperature. Because of that reason, this is not so popular, though some work is going on for aircraft. Most of the aircraft fuel cells are proton exchange membrane fuel cells. The operating temperatures are low. It can be managed. That is the reason PM fuel cells are popular today. So I was telling you that very short duration, you need high power. Then you need capacitor there. Fuel cells, you need for a long duration, small power fuel. Battery is in between these two, okay? And sometimes you can just use a fuel cell and battery. You don't have to use a capacitor at all, okay? And that's most of the operation they are doing like that. So this is will give you an idea of power and energy density, how you can play around. This is an important thing for you. So hybrid propulsion means very high power. You use fuel cell plus battery plus ultra capacitor. High power, medium power, fuel cell plus battery. Low power, just for cruise or so, just fuel cell. This is the power management strategy. That is what being used. And this is the configuration you need to look at it. Okay. Now, so two options we are talking about. One is the battery option, where you have a battery management switching. You have a switching and protection. It is with a motor controller, electric motor and propeller. And a part of this power has to go to DC-DC converter to take care of utility. You need all the other systems, everything should be operated. So you need power for that. They have what you call it. The other is fuel cell power is hydrogen storage. You saw that. Fuel stack is there. DC-DC converter, motor control inverter, electric motor and propeller. But parallelly, I'm putting a battery management, switching and protection, and utility. So this switching and protection connects the what you call fuel cell with the battery, like what I showed earlier. So together they can run the show. Okay. There seems to be that if you have a requirement of range, say about 200 kilometers, so it looks to be required. Anything above 100 kilometers, it looks to be what we'll need, this kind of a thing. That's what the study show. I will show you that. This is what you can simulate the whole thing. I just wanted to show you this picture because a lot of simulation work is going on. And recently, July 2022, about 8-9 months back, they have done a beautiful simulation. Okay. And this, you can look at this one, this paper, and it will give you a very good idea. So you can see clearly the battery, the converter, everything has been simulated. And this is the way we have to do the design. Now, I'm talking about the energy storage, energy conversion and all. Just 1 or 2 words, I want to talk about motors, because after all, you need a motor. For aeronautic and particular full aircraft, you need a motor with high power density, high specific torque value, rotating compatible with propeller, chosen to avoid a heavy gearbox, possible work in overload for a few minutes, and very high reliability. Motor technology has been there, but now a lot of improvements are taking place. You have Types of motor are brushless DC motor, brushless electric motor, brushless BLDC motor, permanent magnet synchronous motor, suited reluctance motor, induction. Induction is one of the oldest ones, and it has an efficiency problem and all. So other motors are used, but there is one more color, high temperature superconducting. If your requirements are something like 1 megawatt, 2 megawatt or more, high temperature superconducting motors are being developed, especially about 2 megawatts. And though for UAM and all, it is no relevance, but you must remember, this is the area where a lot of work is going on and a lot of attention is being paid. And these are the ones possibly they will be used. If you want to have a 100 passenger or a narrow body aircraft equivalent to 737 or A320, that is what's going to be there. Lot of brushless motors for eVTOL available in the market. You all must be aware of that, but I thought for completion sake, I found quite a few are there. They're very small to very high. They're all available, and fairly good weight benefit is there, but a lot of further improvements are also taking place. So AMRAX is one of very popular motors that are available in the market. So you have a motor, you have got energy, but you have to transmit the power. So you need cables. You need also DC-DC or DC-AC converters. So these are the two. I'm not going to spend time, but they are important. They weigh. They have to be done properly. Otherwise, we'll have a safety problem, weight problem, and heating problem. So the switching is what we are talking, DC-DC, DC-AC. There are two things. The mechanical switches are no longer considered good. You have to use a semiconductor switch, and you either as a semiconductor switch is a zero power disconnection for galvanic separation. The same with the plus addition mechanical switch passing the semiconductor for increased efficiency. The option 2 seems to be efficient and saves battery weight, but also adds switch weight, but overall seems to be a better option. And I'm seeing quite a few of our studies where this is what they are using now. So you need to look at it. So very typical IGBT module, what they call it, these solid state batteries, they seem to be extremely popular. There are solid state switches, they are available. These are the kind of things which will be useful to you in your calculation. Now, just before I close, let me quickly go through. This is the Uber in 2016 came out with a mission profile. Most of you must be familiar with that. This is the typical UAM kind of a profile. Ground, hover, transition, climb, departure, acceleration, climb, cruise, descent, all these things at what altitude, what speed they have given. And they're talking about 60 miles, which is roughly equal to 100 kilometers, and with a diversion of 10 kilometers. This is basically the kind of thing what we are looking at. What are the things? They're talking about range, they talk about takeoff, they talk about reserves, they talk about repeatability, and they're talking of battery rapid charging requirement, minimum state of charge for discharge, very important. I had already spoken to you. Minimum reserve state of discharge and battery floor. These are the kind of things they're talking about. Okay, I'm not going to spend time, but these are important for you to remind. And there are what you call safety requirements, noise, energy storage, skyports, charging infrastructure, pilots, network communication, payload. All of them are available. Okay, but they are important for you to know what they are talking. It's the very first document came about 5 years back, which has really helped a lot of studies to be done. Okay, a lot of changes have occurred, but it's a good document to look at. So finally, what are we looking at? Your input is a mission, payload requirement. You have a eVTOL configuration, baseline configuration, a powertrain architecture, propulsion architecture. Then you do the sighting. eVTOL sighting, power and energy estimation, weight calculation. The output is a design analysis. This is the conceptual design methodology, what we are talking about. Okay, this is recent paper 2022. I have given the source. You should have a look at it. It's a well-written document. And he's talking now. There is one paper 2021 elsewhere. They're talking US flight segments, typical like what we said, what our other paper what I have shown. He's giving what are the kind of speeds, altitudes, distance, all that kind of a thing. And then he talks about what is the kind of payload. We're talking about a payload of 450 kilograms. If that is the case, he is talking about airframe weight equals about 55% of the weight 60% available battery capacity. That means 25 battery SOC flow. This gives you a rough idea of what are the numbers and either. Okay, that gives you a good. That's why I'm showing you this. That gives you a good idea for what is happening in the world. Now, I wanted to show this because you should look at this paper. A fuel cell battery hybrid system sizing method for a eVTOL aircraft, fairly well written. It's talking about suppose you have only battery, we call the degree of hybridization. Degree of hybridization, one means pure battery. Degree of hybridization 2 means pure fuel cell. You can do an optimization between a pure battery to fuel cell or anything in between. This is the simple formula what he has put there. I thought it is important for you to know this. And it is June 2022, I put 8-9 months back. This came in a AIR aviation form. I thought it is important for you to see this particular thing. It's available in the open source. So this is the typical optimization from configuration, design, and optimization. You can put that, okay? The paper what I talked about, they say from what you call Korean University. So worth looking at. And they have done a very good study. They have done a lot of modeling and get pretty good results. So I thought you could look at that one. I want you to remember this important point. Certificate requirement critical system asks for 2 basic design principles: redundancy and fail-safe characteristics. What does redundancy mean? That in case of a failure of a single system component or function, it can be filled by at least one other independent system. This is what you call redundancy. But what is fail-safe? The fail-safe requirement, in addition, assures the initial failure is contained as no adverse effect on other systems. Both are important for you to design your vehicle. Both must be taken into account. If there is no redundancy, it is not acceptable. If it is not fail-safe, it is not acceptable. So keep this point in mind, and this will help you in designing something which can be considered from an operational point of view. So this is what I was thinking I should present to you. That these are the typical configuration. All of you must have seen that. Okay, these are the 2 configurations. So I thought it's pretty popular. And these are the kind of configurations where we can study, and looking at both the battery power, battery plus fuel cell seems to be other option worth studying. This is what I thought would be important to you. So this is what I wanted to convey to you. I hope I've been able to convey a few points important for the propulsion. Thank you.
Thanks a lot, sir. What we will do now is we will open up the floor for any questions or any doubts that people have. Okay, so the floor is open. I would request participants, either you can just raise your hands or we can just allow people to unmute themselves and start speaking.
Professor Panti, if you can coordinate.
Yeah, I'm doing that, sir.
If you can bring to me.
Yeah. I'm just requesting.
Yeah, good. Can I stop sharing?
Yeah, you can stop sharing. You can stop sharing, and we will wait for participants to go ahead with.
Yeah.
Yes, there are 32 people in the meeting.
Yeah.
Together. I noticed that they are from different teams. That's very good.
From different
groups. So, different teams are there. So students have any queries, or if you would like to ask anything, please feel free. And this is open to everyone, not only the students. I see Dr. Pankaj Priyadarshi and also Dr. Ramchandra. Anybody would like to comment, because we have got a nice overview of how to go about doing these things, and also some very specific papers have been referred to, which will be extremely useful, because
that is why I referred that. Some main paper, they will refer another 2-3, all are available, but they will help you in doing a good design.
Exactly. These are recent papers and very contemporary, relevant to the problem that has been given. Yeah, I think people will take some time.
Okay. Your my only request is some paper somewhere I might not have very clearly given a reference and all. but we can know that. So it could be for private circulation, because unless we properly referencing done, some of the pictures you have to take the permission from the author. We can't put it in an open domain, but private circulation we can do. Is it okay, Professor Pant?
Yeah, it is sure.
Surely. I'm not taking the permission from authors quoting their figures.
Exactly. But if there is any student who would like to receive, okay, so we have the first question now from the Phoenix team. Please share the PPT file, sir. It would be of great help if you do so. So we will request Dr. Kota to give the authorization to share this PPT with
the understanding it is for private use only.
Yeah. So you have to give an undertaking that it will be only used for your private circulation.
Some of the figures I have quoted directly, which I have not yet taken the permission of the authors.
That's right. So we will be happy to share the PPT. We will give you a PDF file, and we'll do it only if you send us a specific communication saying that I understand that this is only for private circulation, and I undertake not to share it in public forum. Once we get the undertaking, we will be happy to. Just to avoid the legal hassle. Exactly. We don't want our patron to be in legal trouble because of his attempt to help you out. But right. Happy to share. Yeah. Okay. So, in fact, the PDF version is with Professor Pant. You can directly write to Professor Pant and get it. Yes. So, the first question from Team Strider Shashwat is, I'll just read out for you, sir. So, he says that for high threat requirements like fighter aircraft, is electric aircraft feasible as the payload is major factor there? I was always fascinated by the idea of electric ducted fan. No, but as it stands today, with the technology being available for next 20 years, fighter is not a candidate for electric propulsion. Okay, fighter is not. But passenger aircraft, yes. OEM, small, okay, that is there, but not fighter, because the thrust to weight ratios of the fighter and all are extremely high. So it cannot be done by this. Exactly. See, in a passenger aircraft, I need a thrust to something like 0.4, 0.35 and all. Here I'm talking about 1.1 and all. So not possible. Not possible. No. So 20 years you can forget. Yeah. So participants, please note, Dr. Kota might be well known for the LCA, but he's championing a transport aircraft for India. And, we have it from literally the horse's mouth that for high performance military aircraft, we are very far away from an electrical or fully electric powered aircraft, even hybrid. It's very difficult. Hybrid also not possible. Need the very high thrust to weight ratio required. Okay. All right. Very nice. Again, the next question is, okay, he says he's a big fan of your work because he has very sweet of you. Now we have to make a UAM and then a passenger aircraft. Okay. Yeah. And this should meet not only India's requirement, world requirement. That should be our target. The whole globe is looking at sustainable aviation, which is a very important emerging research area. And I'm more than convinced it is well within our reach, and we should start working. I hope the teams who are working do a good professional study. But this talk is primarily to help you to do a professional study. Exactly. Okay. So,
Sir, Dr. Pant Ramchandra here.
Yeah, you can go ahead, sir.
Sir Ramchandra, good evening, sir. With the limited use of these batteries for small UAVs, we found that as you go to about a kilometer or two, the battery performance comes down very drastically because of the altitude and associated temperatures. Yeah. So, any idea how this big power stacks?
What you have to do is, Dr. Ramchandra, the battery management is critical. You cannot go below 20% of the capacity. Right. And if you want to use for a prolonged range, because the charging time up to 80% is reasonable. But if you want to charge beyond 80%, again, it takes a long time. So for a UAM kind of thing, they talk about 20 to 80. That means only 60% of energy, so-called energy capacity is a usable capacity. Okay. Second, temperature control, cooling may have to be done. So these are the kind of things we need to do, but it is all perfectly feasible. But
Right.
you have to slightly oversize it to get the
Yeah.
kind of performance. But one good point is what was about 150 to 200 watt hours per kilogram is already
Right.
come to 300 watt hours per kilogram.
Right.
And if you take about 30% for the packaging, we are still about 200, 250, we can get it. My understanding is in a matter of another 5 years, with solid state batteries, we can reach about 600, which is
Right.
good. With that, we
Right.
can make even small passenger aircraft. No problem for UAM, but solid state batteries, there's not enough time to talk about type of batteries and all, but that
Right.
seems to be a direction. And
Yeah,
fuel cell
possible.
also
Yeah.
seems to be a good thing, and we
Yeah.
need to pay attention to fuel cell. That is
Yeah.
the
Very
reason
good.
why I presented that.
Yeah,
Very
if I,
good, sir.
if I can
Thank
just
you.
if I can just add something. See, there was a dedicated talk on various types of batteries last year in the last year's NACDeC by one Mr. Murthy. He had actually covered in all detail, and that particular talk is also available on our NACDeC website. In fact, this
I
talk,
have quoted that Ajay Mishra's paper
yeah,
on types of batteries and all, that is available. We can refer. It is available in the what you call open source.
yeah,
Okay, it's worth looking at it.
yeah. So, sir, there are a couple of
Sir
questions.
Pant, end
Yeah.
of April to 27, 28, in our electric aircraft workshop, what we can do for all of our students, we can connect them through a hybrid route. And Ajay Mishra is giving a talk.
Okay.
Okay, so it is good, worth listening to. Okay,
Yeah.
and there is a talk by Rajamani on what you call certification challenges. Okay, and on motors there is a talk by Professor Aran. It may be worth listening to. And whichever student, there is no what you call money involved. You only have to register. I think we can do that. Professor Pant, if you think okay, we can do that.
Yeah, we will announce it in our WhatsApp group, etc.
Yeah,
Now
we can connect to them so
Yeah.
that they can take the benefit of that workshop.
Sure. So in between, there are three questions. I'll just
Ah.
quickly go through. Two of them are related. So Akshay Jain, who is from IIT Bombay and an Air Force officer, doing MTech right now, he says, you spoke about battery consumption simulation. He wants to know if there is any open source simulator available for battery consumption simulation.
That what you call Seoul University paper, he has used a commercially available software to do the simulation.
Okay.
And he does a dynamic simulation.
Okay.
I think you can read that one. Okay.
Okay.
It
Same
gives you it is a good source. That's why I felt it should be read.
Right. Same question was also asked by Sujana from Metal Hawks. Can you elaborate more about the simulation of battery system? So as he mentioned to you, the paper by the Korean authors, which he has referred and which we will share with you. By the way, this webinar is also being webcast on YouTube. So it will be available permanently on YouTube. And we are also taking a copy
those
of
papers. If you have any problem, you get in touch. Those papers we can give it to you.
Yeah,
okay?
we can.
And they refer to some commercial software for modeling and simulation.
Yeah.
We can use that. Okay.
Okay. Then there is a question from Shashwat again asking, most of our aircraft operate at high altitude, hence lower temperature and lower operating pressure. So for fuel cell or even battery, will performance degrade during the cruise?
Yeah, in the sense, see, theoretically a battery is impervious to environment. Okay. But then battery management system has to keep it at a particular temperature. If temperature is too low, battery performance comes down. So battery management system has a heater which will keep around 40 degrees or so. So from that point of view, yes, if you don't have a temperature control, it will deteriorate. Okay. So that has to be, but there's hardly any battery today without battery management system. Okay. So it is a fully tackleable problem, not an issue. Okay.
Okay. Okay, so the answer is that yes, you do require battery management system to maintain the temperature within a particular band.
Not only that safety issue, it is vital to have a battery management system.
Yeah. Right. So all students who have flown remotely controlled aircraft, you know that with every RC motor, you have an electronic speed controller. that is a kind of a management system for the motor.
So there is one is a motor controller for which will control the motor, propeller and all. Another is a battery management. They are two independent things.
Correct.
You must have a battery management system. You also have to have a motor motor controller. Okay. Both are required. Without that, you can't make an aircraft, right, whether UAM or anything.
Correct. Okay. Any other question before we wind up? It's already 8:10. I think Dr. Pankaj Priyadarshi, I think you have unmuted yourself. Would you like to ask a question, Pankaj?
Hello, sir.
Hi,
Am I audible?
Yes.
Hello, sir. Good evening. Really enjoyed your talk. Sir, I was wondering, do we have commercial vendors which can give specific battery solutions for, commercial aircraft? Or do we still have to sit down and configure all these things ourselves?
Commercially available.
As a solution, one can subcontract.
They'll give battery plus battery management together.
Right, sir. Thank you.
But you have to give them your requirement, but they can configure it for you. There are people who manufacture battery. There are people who do battery management system development, but there are people who will combine these two and give that. Okay.
Okay. So it has already.
And they are not readily available in India, but I'm sure with a bit of a push, people will be able to do that. It's not too difficult.
Okay, sir. Thank you.
All right. Thank you so much. Okay.
Okay.
So if there are no more questions, then we will have to wind up this webinar. Normally we do it in 1 hour. Today we have gone a little bit more because we also began a bit late. Okay, but we cannot hold on for a very long time. So if there are no more questions, then okay. So there is another question. As can be seen in HALE UAVs, the use of solar panels for power can incorporate. So can we incorporate solar energy for electric propulsion?
Yes, it can be incorporated. And it is being incorporated by all the HALE fellows.
Yeah, high altitude, long endurance people are
they always incorporate that.
They always incorporate.
You're right.
You need large wing area for that, but
you need only high altitude, long endurance. Endurance is so high, invariably you have to keep a solar collector.
And because of the requirement to loiter, they have a very large wing area anyway.
That is the point. If your wing is small, you can't do anything.
Yes.
For a UAM, you can't do.
Okay. Okay.
Good then.
Okay. So I think we will then wind up the session. I would first of all thank Dr. Kota as always. He has been behind this NACDeC right from day one, supporting all our activities. And it's great to see a very detailed and very succinct presentation on all aspects relevant. So I thank you so much, and also for agreeing to share on a limited, in a limited manner, the material that you presented. With that, I'm going to stop the webinar and requesting participants to tell us about the next topic, the topic for the next webinar. If you tell us in advance, we can approach experts and get them on board. So use our WhatsApp group and use the dedicated email to let us know. I hope all of you are working hard towards your design. We are going to slowly approach the submission deadline. Thank you so much and have a good evening. Thanks all.
Thank you, Professor Pant, for making it happen.
Okay. Thank you. Okay.
Thank you.
Thank you, sir. Good night.
Good night. Okay.
Thank you, sir. Thank you.